This is lesson 2.3.C, slope and rate of change. In this lesson, we will be calculating slope from various representations, and we will be calculating and representing rate of change. Let's first examine slope, and let's look at how we can define slope. Slope shows a relationship between changing quantities, such as vertical and horizontal changes. If you look down at this graph, you can see that our slope represents a change from here, this point down here, up to here. That is a change in our rise, the change in y values. It also represents a change in our x values, going from here to here. That represents our horizontal change, the change in our x values. So it is a rate of change, which is what we're going to be looking at as well. We can also describe it as a change of y over a change of x. And in fact, we also say rise over run. Let's look at the equation for slope. Slope is represented by m in our equation y equals mx plus b, which we are familiar with. So when we write the equation, we always say change of y's. So we say y2 minus y1 over x2 minus x1. Now notice it doesn't matter which of these points we label as x1, y1, or x2, y2, as long as we keep them the same. If these are our 1's, then these have to be our 2's. It also makes a difference that if you put y2 first in the numerator, then you need to put x2 first in the denominator. So this is our equation for representing slope, and that's what we'll be using today. Here's a picture of a vehicle going up a very steep incline, and what I want to know is, how does this show slope? If you want to think of something that you might see every day, you might see when you're driving up I-70 that it says something like I don't know, how about a 7% grade? And it'll say something like, warning, truckers beware, 7% grade ahead. Have you ever wondered what that meant? That means, think about what percent is. We can write this as 7 over 100. That is the same thing as 7%. If we think about that with slope, remember that we said we are looking at our rise over our run. In other words, change of y over change of x. So in this situation, for every 100 feet that a car travels, the car would then go up 7. It may not seem that steep to you, but to a car that can be very steep. So let's look at this example up here. If I were to draw a line here compared to my line here, this could be a very steep incline. Perhaps this is saying that for every 10 feet the car goes this way. It looks pretty steep this way. Maybe it's going up 9 feet here. And in that case, we would have an elevation of 9 over 10, or a slope of 9 over 10. If I were to convert that to be out of 100, I would multiply both the top and the bottom by 10. So let's do that. Let's actually multiply here. So instead of equals, let's see what that would equate to. Times 10 over 10 to convert it to a percent, and we would get 90 over 100. That would be a very steep incline. That would be a 90% incline. Now again, I just roughly put some numbers here. We don't know if that's what it really is, but that's how slope is represented in real life. Let's look at slope on a graph, and you've seen this before, so let's examine. In the past, it's been easy to just count and say, oh, well, it's rise over run. So let's count. We've got 1, 2, 3, 4, 5 is our rise. So we can put 5 here. Over our run, we would go this way, 1, 2. Now the one thing we always have to be careful of is that we are writing this as either a positive or negative slope, that we are representing this correctly. So when we read our graphs, we read our functions here, we always read from left to right. So if I go from left to right, I would be starting up here, and I would be going in the down direction. So this is a negative sloping line. Now there's another way to find slope in case for some reason our points are very far apart and we just want to do it algebraically. Well, if we look at the coordinates of this first point, we went over -2 and up +2. So the coordinates here, and I'll write these on the graph, are -2, 2. The coordinates for this point, well, we didn't go left or right in any direction, so our x-coordinate here is 0, but then we went down 4. If we use our equation, the change in y over the change in x, like we did before, y2 minus y1 over x2 minus x1, let's see what we get. So I'll go ahead and start with the ones down here. So -4 represents our y2, minus 2, which represents our y1. And then down here I have 0, which represents my x2, minus a -2, so I have a double negative here, and that represents my x1. So let's do the math. Remember that when you have two negatives, you can make one turn into a plus and then make the other number negative in order to better see what you're doing. In this case, we are adding two negatives, so we would end up with -6. On the bottom, we can do the same thing, so I'm going to turn this into a plus, which means I need to turn that into a plus. Now I have 0 plus 2, which is just 2. I'll go ahead and divide this and get -3. So my slope is -3. Now if you notice, I must have made a mistake because when I counted, I got -5/2, and when I did it algebraically, I got -3. So let's double check. Let's double check our math. Well, here's where the problem is. 1, 2, 3. This point is not at 0, -4. This point is at 0, -3. Okay, so if you have a way to double check, then you can make sure that you are doing this correctly. So this should be at 0, -3, which means that my equation is off here. So let's actually start over again. Let's verify our slope. So let's start with -3 minus 2 over 0 minus a -2. Okay, so all I've done is changed this number from a -4 to a -3. And again, let's make this be a plus and a minus, and we get -5 on top. Same thing here, let's make this be a plus and a plus, and I get 2 on the bottom. Now I know I'm good because that matches my counting. So my slope here is -5/2. Okay, let's continue on. And let's actually just go from 2 points. So say you know 2 points and you want to find the slope, we can use our algebraic method in order to quickly find the slope rather than having to graph this every time. Okay, so in our first example, again, it doesn't matter which way we start. We can define y2 as 8, or we can define it as 1. I'm going to go ahead and use the 8. So our slope in this example would be 8 minus 1. Right, here is our y2, we are saying. Here is our x2. And over here, I'm saying that this one is x1, and this one is y2, or y1. So we have 8 minus 1 over 4 minus a -6. Subtracting, I would get 7 over, I'll turn these both into pluses, 10. So my slope is 7/10. All right, number 2. So again, I'll keep these as my y2 and my x2s, and I'll go with -4 minus a -3 over 5 minus 2. Okay, I have a double negative, so I'm going to turn this one into a plus and that one into a plus, and I'll get -1/3. There's my slope. And the last one. I have 1 minus a negative 2 over negative 2 minus a negative 2. Okay, I'll switch my negative to a positive, which means I'll switch that one to a positive. I'll do the same thing down here. Let's see what I get. 3 over 0. So that should give you a little bit of pause. Can you divide by 0? You should say no. No division by 0. So this slope is undefined. Can you predict what type of graph this would look like if we have an undefined slope? Let me show you. So I'm going to pull up a graph and then we'll plot these points. Okay, and here's my graph. Now let's plot the points on the graph. I've got negative 2, so I would go over here to negative 2 and then down to negative 2 and put a point. And then I've got negative 2, comma 1. So I'd go over to negative 2 and up to 1 and then put a point. Now let's connect our dots with a line. And if you see, we have a vertical line. And let's adjust it a little bit so it's straighter. So an undefined slope means we get a vertical line. And if you look at that, that is not a function. Okay, because the equation for this, if you remember from an earlier lesson, would just be x equals negative 2. There is no y in this equation. It is therefore not a function. So anytime we have division by 0, or we have an equation that's x equals negative 2, that is not considered a function. Okay? All right, let's move on again. Let's look at some rate of change. So rate of change, we said earlier, was in fact slope. So we're just going to find slope. We want to determine the rate at which the airplane descends. So all we're going to do is find the slope from a table. You have experience finding slope from a table. All you did before was find the change in our y value. But let's look at our x value on this, our time. It does not go up by 1 each time, like the other tables you've seen previously. So we'll have to use our equation, y2 minus y1 over x2 minus x1, to actually find the slope. But since we're doing rate of change, this implies we have a contextual situation. So we need to identify the independent and dependent variables for this. Well, if we look at our table, those are actually identified for us. So our independent variable, it says, is time. X is always on the left, remember that, and y is always on the right. So our independent variable is time, and our dependent variable is elevation. And this will be important when we finish our problem and we include our units. Okay, so elevation represents our y, and time represents the x. Now let's go ahead and find our average rate of change. We'll use our equation. So we have m, which is our slope, equal to y2 minus y1. Now it doesn't matter which 2 points we pick. I can pick this first point, I can pick the second point, I can pick any 2 points. So I'm going to go ahead and choose this point here to be my x1, y1, and I'll choose this point here to be my x2, y2. Okay, so these are my ones. If I plug those in the equation, I will have 27,500 minus 29,000 over, and I will start with my x2, and that would be 5 minus 2, which is my x1. Now I choose 2 points that maybe are a little bit more difficult. You could always choose 0, 30,000, and then 2 and 29,000 to compare. Remember, if we look back at how we define slope, slope is defined as a comparison. Let's actually look back at that real quick. It's a relationship between changing quantities. So a comparison between these quantities. Okay. So we are comparing time to elevation. Now if I go ahead and subtract 29,000 or 27,500 from 29,000, I get a negative number, negative 1,500. And if I take 5 minus 2, I get 3. Anytime we are working with rate of change, we will never leave our rate of change in this format. We will always divide the numerator by the denominator, even if it doesn't come out even. In this case, it does come out even. We get negative 500. And because this is rate of change and we're dealing with an actual situation, we need to say what that 500 represents. Well, remember this is like 500 over 1, so we need something to describe our y's on top, and we need something to describe our x's on the bottom. Well, we said y represents elevation, so our plane is losing 500 feet of elevation, so this represents negative 500 feet, it's in feet, of elevation per, which means over, per minute, which is our time. So I'm just going to say per minute. So this means that our airplane descends at a rate of 500 feet per minute. It loses 500 feet of elevation every minute. So whenever you're doing rate of change, make sure to divide out your final answer. Do not leave it as a fraction, and include your units. All right, let's look at a final example here. All right. In this example, we are not given a table of values to choose from. We are actually given the 2 points that we will use within the problem. So in this problem, it says a car is 200 kilometers from its destination after 1 hour and 80 kilometers from its destination after 3 hours. The way we would start this problem is we would go ahead and write these as coordinate points. So given our first set of information, after 1 hour the car is 200 kilometers from its destination, I'm going to put the 1 here and the 200 here. And the reason that I did that is because typically time always represents our x value, our independent variable. We don't control time. So after 1 hour, the car has traveled 200 kilometers. And then if we record our second set of points, after 3 hours, the car has traveled 80 kilometers. Okay, once I have coordinate points, it'll be easy for me to identify the independent and dependent variables. Well, we know that the independent variable represents x, and the dependent variable represents y. Y depends on x. The distance we travel depends upon how many hours we drive. So we already said that our independent variable is time, right? It's hours. And our dependent variable then is going to be our distance, so our kilometers. The kilometers we travel depends upon how many hours we drive. Now let's go ahead and find our average rate of change. I'm going to choose this, I'll go ahead and choose the top one to be x1 and y1, and the bottom one to be x2, y2. But again, it doesn't matter which way you do it, it'll still come out with the same answer. So on the top, I will have 80 minus 200, and on the bottom, I will have 3 minus 1. So remember, because I used the 80 first, I also have to use the 3 first on the bottom. Subtracting 80 minus 200 means I would get a negative 120 on top and a 2 on the bottom. So again, this is a rate of change. I need to go ahead and divide these out, and I will get negative 60. So what does that mean? Well, remember that we have negative 60 over 1. Negative 60 represents our kilometers, and the 1 represents our hours. So what this problem is saying is that it says a car is 200 kilometers from its destination after 1 hour and 80 kilometers from its destination after 3 hours. So we are getting closer at a rate of 60 kilometers per hour to the destination. So we started off far away, but each time we get closer and closer and closer. All right, and that concludes our discussion on rate of change and slope.